Okay, so today is probability, and we got a little bit of a late start, so we're gonna go through that. I don't want to rush this any more than I usually do, so I thought maybe we just shave a minute or two off each break, if that's all right, so we can finish on time. Cool. Because it's already going through pretty fast anyway, isn't it? Yeah, I hope you brought your jars.
Right, that would be my normal operation.
Okay, so introductory concepts. So we'll do some introductory probability theory. So just the basics. That includes some set theory, some basic arithmetic, learn about independence, probability measure, mean, variance, and standard deviation of data sets. Then we'll hit random variables, which is what we'll. This is like this. I think this is the set. This is the core of today's topic. Is talking about random variables, but we got to do this first. So we can talk about random variables, and then we're going to talk about 4 specific types of random variables and how they're distributed, what their probability distributions are. The binomial distribution, the Poisson distribution, the exponential distribution, and the normal distribution. Talk about when they occur, how they're used, what their properties are, and stuff like that. So that's coming up. So, and in the meantime, we'll have to do a little bit of integral calculus, just enough to figure out what we're talking about. All right. But first off, we'll just talk some basic stuff. So what is probability? So probability theory was developed in the 20th century, really, by, it was developed informally way before then because it was originally used by gamblers to try and understand strategies for playing games of chance. But it was really only put on a firm mathematical footing in the 20th century by people like Kolmogorov in Russia and Solomonos. So the Russians had a big hand in this. It is the mathematics that deals with uncertainty. So trying to quantify uncertainty in a way. So the basic idea of all probability theory is the concept of a random experiment. A random experiment. So examples of random experiments include coin tosses, a roll of the die, or a data channel. So these two are classical things that you would expect. So the outcome is uncertain. A data channel, the outcome might also be uncertain if there's noise in the channel. And so what you get out on the other end might be slightly randomized based on what comes in on the other side. On the front side. All right, so here's the layman's definition of probability. It's the measure of one's belief that a future event will occur. And the word future here is not really completely, that's a little bit too restrictive. Sometimes you want to measure one's belief that a past event occurred based on current situations. So you can actually flip this around. But anyway, it's supposed to be a quantitative measure of one's degree of certainty, one's belief. And we will measure we will assign a number to people's belief, and that number will be between 0 and 1. 0 meaning you are absolutely certain that the thing did not occur, and 1 meaning that you are certain that the thing did occur. And everywhere in between is just going to be some real number in between those two things. So if it's 1/2, that means you are completely on the fence. It could either occurred or didn't occur, 50-50. Okay. So here's some characteristics of a random experiment. You can't predict the outcome. So you perform an experiment, and the experiment has a certain outcome. And typically, you are not necessarily able to predict the outcome with certainty. That's what makes it random. But you should have a well-defined list of what the possible outcomes are. So you should be able to know what the possible outcomes are. So, for example, in a coin toss, we interpret there being two possible outcomes, heads and tails. Okay. Die roll, we think of there being, if it's a standard 6-sided die, we think of 6 possible outcomes, which we might label 1 through 6, depending on how many dots appear on top. In the data channel, well, if we're sending a single bit through, then the possible outcomes, well, there are combinations of things. A 0 could be sent through, and it could get through without change. Or a 0 could be sent through, and it flips to a 1. Okay, and so forth like that. Furthermore, the person on the other end, the receiving end, may decide that the bit is correct or not, and may decide to flip it back again if he or she thinks it's wrong. All right. So you can make a list of possible outcomes, and we should have some intuition or even just some empirical data about what the likelihood of the various outcomes are. Okay, these are the basics that you need in order to understand a random experiment. All right. So the set of possible outcomes of a random experiment, for a coin flip that's heads or tails, we call that the sample space. And we usually denote, in the slides, we're going to denote it by the letter S. In the book and in other places, in the book you have and other places, I usually denote it by the capital letter omega, the Greek capital omega, which looks like a horseshoe. We'll take either one. And an event is going to be some subset of S. So an event is a set of outcomes. We think of the event, we describe the event as an occurrence of one or more outcomes in the sample space, and we usually denote it by some capital letter like A or B. So here's an example with the data channel. So in this random experiment, we will take 8 possible outcomes. And the 8 outcomes are as follows. They're all possible combinations of what bit is sent. So this is a single bit being sent through a channel. What bit is sent, what bit is received on the other end, and what the receiver decides what decision the receiver makes about what he or she thinks was sent. So, for example, here in outcome number 1, a 0 is sent, a 0 is received, and the receiver assumes that a 0 was sent. Here, a 0 was sent, a 0 was received, but the receiver says, I think a 1 was actually sent instead. Okay. In that case, the receiver would be incorrect. And so forth. So we go through all possible combinations of sent bit, received bit, and what was assumed to be sent. And that gives us 8 outcomes. That's the sample space. So we don't consider any other outcomes besides these 8 for this particular experiment. All right. So if we assign labels, so we're just conveniently assigning labels 1 through 8 for the outcomes. So we might be able to list them as a set. So this is typical set notation, where you just list the members of the set and you surround it by curly braces. Okay. And the ... just means, and so forth, 1, 2, and so on up to 8. All right, so here are some events. And we'll usually describe events by giving some statement about the outcome. It's either true or false for each outcome. So, for example, here's an event. The message was interpreted correctly. So we'll call that event C, C for correct. So this is going to be the set of the set of outcomes where the receiver actually interpreted the bit correctly. So he assumed that the bit was equal to what was actually sent. So what outcomes are those?
1.
Well, 1 definitely. 2?
3.
No. 3?
Correct.
No. 6. Yeah, 1 was sent. And an 8. And notice those things don't depend on if the bit was flipped or not in transit. Okay, and it's actually the ones with stars here. Those are the ones that are correct. So this is going to be 1, 3, 6, and 8. Okay, so that is a typical event in this sample space. How about the event? Hold on. Get that out of the way. Stay there. Don't move. Thank you. Okay. A 0 was received. So what labels are those?
1,
2, 5, 6. Okay. 2, 5, 6. Let's do another sample, another experiment. So tossing a die, a 6-sided die. So let's list the possible outcomes. As we said, it's probably just easiest to list it 1 through 6. Those are the values showing on top of the die. Now these are correspond more closely to the actual outcomes. Before, in the previous sample space, we just picked those labels 1 through 8 arbitrarily, just to enumerate them. That's not necessary to do. You could actually list them maybe as bit vectors, like 0, 0, 0, 0, 0, 1, and so forth like that, all 8 of them. Okay, but here the sample space is definitely 1 through 6. But here's an event, a 3 was tossed. So what outcomes are in that event? 3, yeah. Okay. So this is we'll call that N3. And more generally, N sub I, that's the event that an I was tossed, for I going from 1 through 6. And that's just the event consisting just of I and nothing else. This is sometimes called a singleton set, a set with just one element. Singleton events we'll call simple events. An event, if it just consists of one outcome, we'll call it a simple event. Elsewhere, it's sometimes called an elementary event because it has one element. And often we will drop the brackets. If I have a simple event, sometimes we'll just drop the braces around the thing and just use the outcome itself to stand for its own event, its own elementary event. All right, a number greater than 3 was tossed. So G3, greater than 3, what's that going to have? Yeah, 4, 5, 6. Good. Okay. A prime number or 1 was tossed. 1, 2, 3, 5. All right, 4 and 6 are not prime. So, but actually, 1 is actually not prime. But I included 1 here anyway. Yeah.
As we go through the problems for this, is it always going to be these abbreviations for what we're looking for as far as N, G, prime, or is it usual?
These are just going to survive for the next couple of slides.
Okay.
There's just for the sake of the current discussion. But no, these are not universally agreed to. If I decide to do this, I generally won't use these notations. I'll just write out the event longhand. So there shouldn't be any ambiguity. All right. So to deal with events are sets of outcomes. We combine events in different ways. So for example, we might say that this event occurs or this event occurs. Or maybe both events have to occur at the same time. Or this event does not occur. Well, we have to have ways of manipulating sets so we can describe those, so we can combine events into new events. So one way of getting a new event from an old event is called complementation. So the complement of an event A, that's the event that A does not occur. It's usually denoted by A prime, or sometimes by A with a bar over it, or S minus A, or S backslash A. There are lots of different notations for this. This is called the complement of A in the sample space S. it's all the outcomes which are not in A. So greater than 3, if the greater than 3, that's 4, 5, 6. Complement of that is going to be what? 1, 2, 3. Right. It's everything that's not in the event. All right. The union of two events, A and B, that's the event that A occurs or B occurs or possibly both. We include both. And we usually denote it by A with this cup-shaped thing, which kind of looks like a U for union. That's how I remember it. So A union B. Okay, so that's a new event. That's another subset of the sample space. The intersection of A and B, that's the event that they both occur simultaneously. They both occur in one run of the experiment. And that's denoted by A intersect B. So the cup is turned around, it's upside down, and it turns into a cap. All right, so let's take some examples. So C complement, this is back in the data channel sample space. The complement of C, so C was 1, 3, 6, 8. What's this then?
2, 4, 5, 7.
Yeah, 2, 4, 5, 7. And how do we interpret this in English? This is the event that
C does not occur.
C does not occur. Okay, but could you be a little more, talk about the actual channel itself? This is the event that the bit was, this receiver was wrong. Right, the bit was interpreted incorrectly. Yeah, yes, that's true. You could say this is the event that C does not occur, and that explains it entirely. I was looking at something a little more descriptive. Okay. R0. Remember what R0 was? R means received. So this was the event that a 0 was received. Okay. And that was 1, 2, 5, and 1, 2, 5, and 6. So its complement is 3, 4, 7, and 8. And what's an easy English description of this? The 1 was received, yeah, because it's either going to be 0 or 1. You could say a 0 was not received, but that's equivalent to saying that a 1 was received. Right. And so we might call that R1, for example. Let's look at the union of C and R0. So here R0, that's R0 complement. Well, there is C, and there's R0. So what's their union? The union is
1, 2, 3, 4, 5, 6, 8.
Yeah, 1, 2, 3, 5, 6, 8. Right. So it's everything that you find in either of these two sets, or both. It could be in both. And list them out like this. All right, 1, 2, 3, 5, 6, 8. Notice that there are some that are in common, like 1 and 6 are common to both sets, but we only list them over here once. So when we describe sets, duplicates don't matter. Okay, there's no such thing as an element occurring more than once in a set. It either occurs or it doesn't. So duplicates don't matter in sets. The other thing that doesn't matter is it doesn't matter how you list these. You can list them in any order. So we just happen to be listing them in increasing order, but that's just by convention. You can also include you could have included duplicates in that list, but you get the same set without including the duplicates. So why bother? All right. So how about C intersect R0? So this is the event that a 0 was received and it was interpreted correctly. So what's this? Yeah, so this is 1 and 6. So these are the outcomes common to the two sets. That's good. Okay. So the union corresponds to the word or. Either the bit was interpreted correctly or the received bit was a 0. Either of the two. And both, and when we say or, we mean we always interpret it inclusively by default, which means both could happen, and that's still okay. Whereas the intersection corresponds to the word and. You have to say that, bit was received correctly and a 0 was received. Both have to happen. So, two events are disjoint, also called mutually exclusive, if A and B have no outcomes in common. So if you take their intersection, there are no outcomes in the intersection. So there's no duplicates. Then we say they're mutually exclusive. What that means is that it's impossible for both A and B to occur at the same time. Okay. Certain event, an event is certain if it always occurs. The sample space S itself is an event. It's the set of all possible outcomes. This is a certain event because the result of the experiment is one of the outcomes that you listed. You listed the exhaustive set of possible outcomes. So that set itself is a certain event. An impossible event is one that never occurs. And the empty event, which is denoted by this thing or by just curly braces with nothing in between, that's an impossible event. So this is the event with no outcomes. It's a legitimate event. Any questions so far?
So,
Yeah. So one way to say that A and B are mutually exclusive or disjoint is to say that their intersection is the empty event. It's the impossible, which is impossible. All right, so notice, for example, N3 and G3 are disjoint. You cannot simultaneously roll a 3 and roll something greater than 3 in one roll. Okay, you either roll a 3, or you roll something greater than 3, or you roll something else, but you can't have the two. You can't have these two things occurring at the same time. So these two are disjoint or mutually exclusive. These two, they union. If you take the union, that's the certain event. So every time you make a roll, it's either greater than 3 or it's in this other event, perm. It's 1 prime or greater than 3. So notice that, so we have a couple rules to use. So notice that A and A component are always disjoint, right? A cannot both occur and not occur, all right? It's one of the two. So A intersect A complement is the empty set, but A union A complement is always certain. In fact, it always equals S. So no matter what the outcome is, that outcome is either in A or not in A. It'll always, the sky is either blue or it's not blue. That's just always true. All right. So we have some Venn diagrams to illustrate these concepts. So we think of the sample space as the universe. So every set we're going to talk about is a subset of that universe. So S is this big rectangle here. So this Venn diagram suggests that A is a subset of B. A is a sub-event of B. What that means is that any event in A is also in B. There could be events in B that are not in A, but if any event, if that event is in A, it must also be in B. In that case, we say that A is a subset of B, or A is a sub-event of B. Here's the idea that A and B are disjoint. So we think of the outcomes in A as being in the green circle and the outcomes in B as being in the blue circle. So here there are no points. So points in S correspond to outcomes. Here there are no points in both circles simultaneously. So this is when A and B are disjoint. Here's the complement of A. It's the colored region. It's the yellow region here. So that's so it's everything that's not in A. And here's A union B. So it is everything in A or in B or both. Okay. And here's the intersection. A intersect B is just that sliver of things that are both simultaneously in A and in B at the same time. So notice, for example, that the intersection is a sub-event of A. It's also a sub-event of B. Furthermore, A and B together are sub-events of their union. So A is a sub-event of A union B, and so is B. Questions? Is this too basic for people? Is this too basic for people?
No.
Okay, good. All right. That's good.
I don't think that exists for some people in here.
I was starting to feel smart.
You're starting to feel smart.
No worries, sir.
Well, that next slide will cure you of that.
Now everything's normal again.
Yeah. All right.
Getting scared.
Okay. So we've been talking about sample spaces. We've been talking about events, outcomes, and events which are sets of outcomes, and how you can combine events to get new events, and some of the relationships between events. But we've got to bring numbers into the picture at some point because we're really talking about probabilities, and these are numbers between 0 and 1. So a probability measure is a way of assigning numbers to events. So every event in the sample space is going to have a number assigned to it, which we would call its probability, according to the probability measure that we come up with. It's possible there may be more than one possible probability measure, but usually we fix the one that looks correct. Bless you. All right, so probability measure is some function, it's some rule that assigns a numeric value p to every event in the sample space. Different events might get different probabilities. So I'm not assigning the same number p to every event. That's not what I'm doing. So if A is an event, we usually denote the number we associate with it as P of A or per of A using either of these notations. And we don't necessarily what these are depend on the situation. So we have to assign these numbers on a case-by-case basis depending on what the sample space is. But there are basic rules that every probability measure has to satisfy no matter what, and that's what we give next. These are sometimes called axioms, the axioms of probability. So the first axiom says, for any event, its probability has to be between 0 and 1. So that's the basic thing. We're not going to consider probabilities that are outside this range. Bless you. The probability of the sample space, remember the sample space is an event. It's a certain event. We will set its probability to be 1. So the entire sample space itself occurs with probability 1.
Okay.
And finally, the third law, which is really the most important because it allows us to actually calculate probabilities of new events based on probabilities of old events. If A and B happen to be disjoint, if A and B are disjoint events, then the probability of the union is the sum of the probabilities of the two events. So this is called the additivity rule. And it says that if I have two, and it's important these two events be disjoint, they're mutually exclusive. The probability of either one occurring, so the outcome being in either one, should be the sum of the probabilities of it occurring in one plus the probability of occurring in the other. So this is one of the basic rules of probability, that you add probabilities if the events are disjoint. Okay? If the events are not disjoint, they have some intersection, then typically this won't be true. Because if you add them up, you're kind of double counting some. You're double counting some things in the intersection, and for the union, we don't double count the intersection. That's kind of why that's true. So this works for disjoint events. But this is good enough, actually, for all our purposes. All right, so what are these numbers actually? Well, it depends on the sample space. It depends on the situation. We assign them based either on physical reality, observation, or just common sense, or even just fiat. You know, I'm going to say that this event has this probability, and you just have to agree to that. Okay. All right. So let's do. Let's look at one possibility here. So I'm going to erase this. So this blue, this green rectangle at the bottom is a very important piece. It says a lot. And I want to digest it for you, or help you digest it. So we have some sample space. We fix some sample space. And all our sample spaces will all be discrete in the sense that I just have, some finite or even just countable number of outcomes. So here, if I have some finite number of outcomes, I'll label them S1 through Sn. So this is purely abstract. I just have n outcomes, and I'm just going to label them S1 through Sn, okay, in some way. Like we did with the channel, we labeled them 1 through 8. For each I, from 1 to n, I'll let p sub I be the probability of the elementary event Si. So this is an event. It's an event that consists of a single outcome, S sub I. I just took away the curly braces. And I'll just call that p sub I. So right now we're just defining notation. So each outcome, each individual outcome, the event consisting just of that outcome, I'll call that p sub I for the ith outcome. Well, additivity says that if you add the probabilities of all the outcomes, you get the probability of the union of all the outcomes. Well, what's that union? It's the whole thing, right? And we said that the probability of the whole sample space is 1. So what that tells us, first off, is that if we add up the probabilities of all the outcomes, we get 1. Okay. How are we with this summation notation, this sigma notation? Okay. Anyone not comfortable with it? Remember how to use it? So this is this. Read this as the sum from I going from 1 to n of the p sub i's. So this is p1 plus p2 plus p3 all the way up to pn. So additivity says that if we just add up the probabilities of the individual outcomes, we just add them up, we get the probability, we get 1, which is the probability of the entire sample space, which is the union of all these elementary events. Okay? So, that's true not just for the sample space, but let's consider any event at all. Call it E. So E is an event. It's a subset of the sample space. Its probability is going to be the sum of the probabilities of the outcomes in E. So you take each outcome, take its probability, and add them up. And you can add them up because all the outcomes, all these events are disjoint. All the elementary events are disjoint. Nothing, because they only have one element in common. So you can add them up, and so the probability of some event E is just the sum of the probabilities over all the outcomes in E. So the way you read this is the sum over all I, such that S sub I is a member of E. So if you can't read it, it's a little bit small, but that's below the big sigma. Okay. Read this as you're summing over all the i's such that the corresponding event is a member of.
corresponding event SI?
Yeah, S sub I is the corresponding event. So I is running through is going 1 through n. And so I is a number from 1 to n. S sub I is an outcome in the sample space. But we've labeled the outcomes S1 through Sn. So the numbers and the outcomes match up exactly. So here, P sub I just depended, we labeled with a number I. Yeah.
So for instance on this, if S sub I, like it's easy if it's just one item in the set, but if it's multiple bills, you have to do the probability for each value in the set occurring and then sum them.
Exactly right. Yes. So let's say, we'll do examples shortly. But let's say E consisted of 3 outcomes, so like S1, S2, S3. Then the probability of E is going to be P1 plus P2 plus P3. So that's really all it's saying in just some compact abstract notation. That's really all it's saying. So, in particular, so here's a very important special case. Suppose all the outcomes are equally likely. So they all have equal probabilities. In other words, they're all equally probable. That's the word we use. Well, if all the PIs are equal, and there are n of them, and they sum up to 1, what does each PI have to be? It's just 1 over n, right? So each PI in this case is 1 over n. For all I 1 to n. All of the outcomes being equally probable, we call that the uniform probability distribution. Okay, we say that the probability measure is uniform. Okay. And if we have a uniform probability distribution, then the probability of any event is very easy to compute. You're just adding up for all the outcomes in the event, you're adding up 1 over n. So all these PIs are equal to 1 over n. So if there are k of them, you're adding 1 over n k times, you're going to get k over n. So if E consists of k outcomes, or simple events, then its probability is just the size of E, k, divided by n. Well, n is the size of the whole sample space. So it's really the size of E divided by the size of the sample space. That's the probability of E. So it's like, what fraction of the sample space is E taking up? That's its probability, if I have a uniform distribution. The thing about this slide also says, before I go on, well, we'll take a break first, and then we'll go on. The thing about this slide also says that the whole probability measure, you can compute the probability of any event. You only have to know what the probabilities of the individual outcomes are. If you know the probabilities of the individual outcomes, then that completely determines the probability of every event, because you just add up the probabilities of the outcome inside the event. So the entire probability measure is completely determined just by knowing the probabilities of the individual outcomes. So there's a lot less information here. There's a lot less information here than having to record what the probability of every possible event is, and there are lots and lots. There are lots more events than there are outcomes. Okay, so this is nice. This says you only have to know what the outcome probabilities are if you want to compute the probability of any event. All right, questions on any of this? All right, it's a couple minutes early, but let's take a break, and if we can chop it to 8 minutes, that would be really nice. So we can. So about when the hand is on the 7th, on the 7th, or maybe a minute after. Thank you. Maybe all have lunch. You can leave the coffee room. Yeah, I know.
Remembering
making any money off of this? Raise the prices.
Nah, it was just a week and a half something, and like the Snickers was like $6.88, $5.88, and it was like 58 cents each. I just put 60 on there. Just a week and a half stuff in
it's
there.
gonna start that.
You know, do it. You know.
I actually was thinking about just putting like a $5 in and then keeping track myself so I wasn't using $6.
Actually, I did that yesterday. I put more money in there this time than I actually told myself. Like,
Is this just so that we have cash? I didn't know if we were using it for that or if we were using it for like pay for plaques and all this other craziness.
You can.
We can't use this price. Well, that's what I'm saying.
yeah,
25 cents for water, we could put water for like 50 cents. And that's like,
The prices we have in the hall would be like $5 for 2 singles.
Like that.
And then we can just send them to Korea.
well, let's just have to.
Well, you're hey, I'll give you a major review. So I was like, hey, Kevin Hall tell you if he wants both spots in Korea. He wants to occupy them simultaneously and do the job.
Why do we want to go?
Because that's what my list looked like. It was like, yeah, if I could say word, I want to go somewhere I'm helping for a year, which was basically Korean point.
Well, you know, I heard that.
I guess you can not.
Yeah, if you do that, I'm gonna punch you in the dick if you come back here. She's gonna take all your money and run.
Where do you want to go? I wanted to go. Oh, go to Kuwait or something like
Like
that?
one of the most eye-opening things was with paper transfers, like talking about how I've been back in a few years, and like I like this one.
Did you talk to him about?
And he made me have this HRC. This is like in August. He was looking at me. He was, there were like 12 deployable captain slots, and there were like 12 deployable major slots.
And it doesn't matter.
Period. Yeah, like I mentioned, this was before.
Yeah, there's not that
I
much.
started being here, so I said, hey, I've been back for 2 years, I'm like, well, I'd like to deploy. And he goes, yeah, you should want to deploy, that's good. He's like, but beware, there's like 12 for captains.
He went on.
So he's like, it's completely possible that even though you want to deploy, like, you may not.
Even told
Unless
me
something, unless something crazy happens.
it's not necessary to move to people like no learning.
I think about doing Florida.
He's like, I'm not really. It's not like
Staying.
you go to jobs, you go to school, you learn shit. You never learn before. You learn everything.
Well, yeah, you need to get the job in the States, or, depending on where they send you, you may get one where you learn way more than you would at the equivalent job downrange. You're about like in-place systems where I think you can say he worked out a couple of years ago, like when team over 2 and 3, like that's
And also like,
even like the NMB research part.
Hey, let me know if allergy to penicillin is a year
It can,
for overseas assignments, it matters.
Well,
You say no or yo?
yeah.
Is there anything you don't like?
Yeah, I just, like, looking at words on the board doesn't help. You know what I mean?
I was about to get into examples, but if you don't understand a few things, you might still
That's what happened for the rest of his life.
Explain this.
back to you. This is your sample. Each one of these individual little essays can be summed one out. Remember the dice 1 through 6.
So with the dice example, what would the sample set would be like?
So if you had dice and you had 1, 2, 3, 5 plus 6. This is your sample space. It just so happens that it works out really well for numbering. You can just pretty much put brackets around it.
So sample space is all outcomes.
Possible outcome. Single outcome. And then he starts talking about it. And that can get a little confusing. Because then you're like, okay, he talks about the, these as events. He's not actually talking about these events. They're still just outcomes.
Right.
An event can be, as he said, a single event, which means that it contains only each sub one, the event that only one event.
Right. Like roll through.
Or in this case, like one yeah, whatever. Now,
Sample set outcome.
that's the sample set of this now.
I assume that.
Times one.
No matter but you'll definitely get that.
It's kind of like you have a you want to think about it?
Yeah, because that's all we turn. That's all I turn.
Think about a bucket of water.
Oh, the whole thing.
And that's your sample set.
I did the whole thing and then I rewrote.
A small amount for each one is an outcome. Or maybe a bucket of ball.
That's how I wrote it.
And depending upon what cup you hold in an event, you can pick out one, or if you use a bigger cup, it maybe says, hey, what about all the events greater than, let's say, greater than, like he said, 4, 5, and 6. That event contains these 3 outcomes. Or these 5. Now this, right now what we're talking about is, as I said, uniform distribution, which means that each one of these has, are you good with this? Okay. Wow. I hope that clears something up. Maybe not. No? I'm sorry. I tried. You helped me not so.
Oh, good.
Once again,
Snickers. Because
Okay,
they
real
took
quick,
the game
for next
or
Thursday,
diabetes
those interviews,
frightened me.
We got them from like 08 up until we're supposed to go over to the Battle Lab at 1300. It's 15 minutes a person. You cannot go over. There will be a timer. You'll get 15 minutes, and then you're done. So make sure whatever you want to talk about, you have up front. If there's anyone in here who doesn't want to meet with McNeese, let me know. That should be it.
Like maybe people that already have their assignments. And we can find
If
that
you
time
don't,
out.
if you don't want to talk to him because he's going to come in on that Monday, we're going to do a class, whatever. So if no one has anything they really want to talk about that's not going to be discussed as a big group, then just let me know. But otherwise, I'm scheduling everybody for a time.
Awesome. All right. So we're back. Okay, so all of this abstract stuff, we'll do an example. Okay. So here is a typical probability measure. You have a single 6-sided die, and we'll say that the die is balanced if every outcome 1 through 6 has equal probability, equally likely. So before we just talked about a 6-sided die. That didn't say anything about the probabilities of the outcomes. Here we are saying that the die is balanced. So balanced is a keyword, means every outcome is equally likely. So every elementary event is going to have a probability 1/6. So this is the uniform probability distribution for this experiment. So every outcome has probability 1/6. So what's the probability of G3? Or 1. Okay, yeah. So G3 is what, 4, 5, 6? So that's 3 elements. Okay, so you take 3 divided by 6. That gives you the probability. So in a uniform distribution, to get the probability of any event, you take the size of the event divided by the size of the sample space. So this G3 has 3 elements. So 3 divided by 6, which is the size of the sample space, gives you 3/6, or simplifying that 1/2. What is probability G4? You can figure out what G4 is. How many outcomes? 2. Okay, so the probability is 2 divided by 6, okay, or 1/3. How about the probability of perm? 1, 2, 3, 5. So 4 divided by 6, or 2/3. Okay. The uniform distributions are particularly easy. So that's nice.
So can you explain the from?
Perm? Yeah, perm means 1 or prime. So perm for prime, I guess. This was 1, 2, 3, 5. So 2, 3, and 5 are all prime. Okay, they're prime numbers, and 4 or 6 are not prime. And I just threw in 1 just for no good reason. All right.
That's that fiat.
Yeah, that's that fiat I'm talking about. Just, I'm defining it this way. That's the way it's going to be. I'm the decider. All right. Let's take example 1. Suppose the probability distribution was determined experimentally. So now I have, let's go back to our channel. So I have 8 outcomes. And maybe what we do is we run this experiment. So here's another interpretation of probability. If you run the same random experiment independently many, many, many times, let's say 1,000 times or 1,000,000 times, and you tabulate how frequent each outcome occurs, you take that, you divide by the number of trials, that is a good estimate of the probability. You're saying that this event occurs roughly this fraction of the time if you do lots of trials. So using statistics and using experiment, running the same random experiment many, many times, this gives the relative frequencies are proportional to the probabilities. This is the best way of interpreting probabilities in the real world. They're the expected fraction of the times you get a particular outcome or you get a particular event.
Does it have a name like non-uniform distribution or non-uniform probability distribution?
Well, non-uniform just means the probabilities are not all equal.
So
okay,
it could be that.
So here,
Or it might not.
if we run lots of experiments and we, for example, notice that 1 occurs 16 30-seconds of the time, which is 1/2. But the other ones are much less likely, except this one, which occurs 10 30-seconds of the time. So this is definitely not uniform, right? Some events, some outcomes are more likely than others.
But it could be if, for some chance, you experimentally went through and they were all 1/32. It would just be.
Yeah. So if they're all, well, then they have to be all 1/8 in this case because they're 8 outcomes.
Roger.
But if they're all 1/8 or close to it, then you reasonably say, okay, I think that the distribution looks uniform, looks pretty uniform. But of course, there are always going to be these anomalies here. You'll never get exactly the right number when you run these because it's always uncertain. But the more times you run the experiment, the closer the fractions will be to the actual probabilities, and so the more precise you can estimate the probabilities. All right, but here we do something, and it's very highly skewed. It's not uniform. So this event occurs much more often than any of the others. All right, but if that's the case, then we have to fall back on our summation rules for computing the probabilities of events. So what is the probability that the bit was interpreted correctly? So let's remember what that was. That was 1368. So this is not uniform, so we have to go back and we have to actually just add up the probabilities for each outcome, and then just take the probabilities for each elementary event and add them all up. So that's going to be 16 30 seconds plus 1 30 seconds plus 1 30 seconds plus 10 30 seconds. What is that? 28 30 seconds. Yeah. So adding those all up, 28 30 seconds, or in simpler form, 7/8. Okay. Sanity check here. The number that you get should be between 0 and 1. This is.
It's going to happen in
But
this
otherwise,
universe.
we're told to give 110%.
Yeah. You should tell them that's wrong. You cannot give 110%. You can only give 100%. That's it.
You can't even give 100%.
The first person who says that in or a freaking probability.
Yeah, that's.
So you
That's.
21. So if you're not 10% of the time of life, so it's not right.
Okay. Are not. The 0 is received. So go look through to see what was received. So that's 1, 2, 5, and 6. So what that's going to be, that's probably 1, 2, 5, and 6. So what is that? 19. And that doesn't simplify. All right, the probability of the intersection. So what's the intersection here? Just 1 and 6. So that's going to be the 16 plus 1, that's 17. Okay. Notice if one event is a sub-event of another, so it's entirely contained inside the other, the probability of the sub-event is going to be less than or equal to the probability of the bigger event, right? Because you're adding up, say, fewer outcomes. So this is a sub-event of both of these, so this probably has to be less than those two, but okay. All right. Here's some more useful properties of probabilities. Well, it's actually what I just said. If A is a sub-event of B, then the probability of A can't be any greater than the probability of B, and it's usually less. This is called sub-events. The probability of A complement is 1 minus the probability of A. You can see this because the probability of A and A complement, they're disjoint. So, but they union to the whole sample space. So the sum of the probabilities is 1. So the probability of A plus the probability of its complement has to equal the probability, has to equal 1. So this has got to be true. This is sometimes called the separation. The probability of A is the probability, if you have two events A and B, and you want to add up the probability, you want to get the probability of A, that you can get that by taking the probability of A intersect B and add to it the probability of A minus B. So A minus B is, these are all the outcomes in A which are not in B. Maybe I should draw a Venn diagram for you on this one, because it's worth doing. So here's A. And here's B. Well, here, this is A intersect B, right? It's that middle piece. Okay?
The other way.
Okay. What's A minus B? Use red. These are the points in A which are not in B. So it's going to be this left-hand crescent over here. So this is A minus B. Well, here, it's pretty clear from the diagram that A is the union of this piece and that piece. And there's no overlap between those two pieces. They're disjoint. So additivity says the probabilities add, and the probability of the big circle is the sum of the probability of this thing and the probability of that thing. Okay. This is useful because sometimes you know what the probability of A is, say, and you have other reasons to know what the probability of this is, the intersection, and you want to find that. And this rule will give you that immediately, okay, for example. Or you know the probability of both of these pieces, and you want to find the probability of A. So this rule is useful for that on occasion. Okay, we call it the separation principle. Here's the union principle. The probability of a union is the sum of the probabilities, but then you subtract off the probability of the intersection. So here, A and B are any two events. They don't have to be disjoint. And we're expressing what's the probability of their union. Well, it's the probability of A plus the probability of B, but then you subtract the probability of the intersection. So back in the Venn diagram, the union is the whole thing, right? It's that whole area. You think of the probability as sort of being like proportional to the area. That's the probability of the union. Well, how can I get that union? Well, I could take this left circle and add the area of the right circle, but when I do that, I'm double counting the area of the intersection. I'm counting that area twice. So I just subtract off one of those counts. And now I'm counting everything here exactly once. This piece, that piece, and that piece is all just counted once. That's why that's true. Okay. I think Venn diagrams are a great tool for understanding how these probabilities work. The probability is some kind of measure of the size of the set, how big it is. Okay.